So, we have discussed the solution of axially symmetric flow over slender bodies of revolution, and in that context we consider an example flow over a cone, and for which we got the complete solution, and for any cone within the framework of small perturbation theory, and then approximated that solution for small slender bodies. However, instead of getting a solution for a particular problem and approximating it for slender bodies, it is possible to introduce the approximation in the solution process itself and get a complete solution for any arbitrary slender bodies. And we will use that method to find the solution about any arbitrary profile in first axially symmetric flow and then possibly in asymmetric flow with cross flow. However, we know that cross flow solution can straightway be obtained from the axially symmetric solution, and we will use this approach to evaluate the forces that are acting on any slender body. So, first of all, let us consider the forces that are acting on a axially symmetric flow or bodies emerged in an axially symmetric flow. So, forces acting on slender bodies of arbitrary profile. First, let us consider axially symmetric flow. Assume this body to be axially symmetric and the flow is along the axis. Now, if we consider any small axial section over which the radius, or we can say the cross sectional area, is increasing slightly, then we can see that the pressure that is acting on this strap, where we have m infinity is the free stream speed, when the free stream pressure is p infinity, and on this section the pressure is acting p, and we have seen from the earlier solution that the pressure varies gradually over this length in an axially symmetric flow over a cone, which we can say may be the general result for a general profile. Now, we can see that the pressure distribution is symmetric about the upper half and lower half, that is pressure has a top and bottom symmetry. Since pressure has a top and bottom symmetry, consequently there is no lift force. Consequently, there will be no lift force. However, we can see clearly that the pressure is not symmetric about front and rear. But drag exists as there is no symmetry between front and rear. And so, in this case the force evaluation of the force is basically determination of this drag force that acts on this body, and we will now try to evaluate this drag force. Now, the general solution for this problem, as we have already evaluated, zero to x minus beta r function of xi d xi, the source strength distribution divided by the kernel x square x minus xi square minus beta square minus r square, where beta square is m infinity square minus 1. Now, it may be recalled that we introduced a substitution and simplified this integration earlier, because this integration has a singularity at the upper limit. It is an improper integral, and use of that substitution make it possible to evaluate this integration. However, for any arbitrary Slender bodies, in this context we do not make use of that substitution to evaluate this integral. Rather, we split this integral in two parts. We split this integral in two parts phi, which we are omitting this functional representation x r all the time for convenience, is that means the upper limit we make it x minus beta r minus epsilon, where epsilon is a small number. Minus this is just to avoid the singularity at the upper limit. We have reduced the upper limit by a small number epsilon. A small number which you introduce, so that there is no singularity in this integrand. However, in this part the singularity is still there. Now, since this integrand is not singular, we can expand it in the power series of beta square r square. So, with this the integrand is not singular, not singular in its domain, and in powers of beta square r square. Now, if we integrate this function, that is 1 by root over x minus xi square minus beta square r square, that is x minus xi square minus beta square r square to the power minus half. This can be expanded as a binomial series, and assuming slender cone, that higher power of beta square r square can be neglected. This gives one by x minus xi plus half beta square r square into 1 by x minus xi to the power 3 . Now, then this first integral can be integrated term by term, that is by okay, we had the and this becomes then f 0 log x minus f x log epsilon plus f prime xi log x minus xi d xi plus epsilon f prime x log epsilon a. This is for the case when beta r approaches 0, that is for slender bodies. So, this is where we introduce slender body approximation. For the second integral, we introduce same substitution which we introduced earlier, that is xi equal to x minus beta r cos hyperbolic sigma. So, for second integral, use xi x minus beta r cos hyperbolic sigma as before, and this gives x minus beta r minus epsilon to x minus beta r, sorry, f xi cos hyperbolic inverse beta r plus epsilon by beta r equal to function of x minus beta r cos hyperbolic sigma d sigma. This integration of course we carried out earlier. So, we can use those result, and this gives f x cos hyperbolic inverse beta r plus epsilon by beta r d sigma minus beta r into 0 to cos hyperbolic inverse beta r plus epsilon by beta r into f prime x cos hyperbolic sigma d sigma. Plus higher order terms in beta r. Assuming beta r 0, that is for slender body approximation. This gives log by 2 beta r plus f x log epsilon minus epsilon f prime x. Now, if we combine these two, we get the potential. So, we have phi x r equal to minus. See, all these terms in both the integration what we have carried out will become negative, because in the definition of phi the integral are preceded by a negative sign. So, this makes minus f x log 2 by beta r minus 0 to x f prime xi log x minus xi d xi. You can see that the terms containing epsilon can be made to vanish if epsilon is approaching to 0. Now, if we consider a pointed body, made to 0, considering pointed nodes, and this eliminates the f 0 term present in the first integration. The term f 0 log x present in the first integration is made to 0 by assuming that the body has a pointed node. So, that f 0 is 0, and this then is the. So, what we get is the potential for slender bodies with pointed nodes, and here it is for any general arbitrary slender bodies. Now, we know that this potential function must satisfy the boundary condition. Now, first of all, let us evaluate what is v. The radial component of velocity is obtained as d phi d r, and this becomes only the first term here is a function of r. So, this can be easily differentiated, and the result is f x by r, or f x equal to v r. Now, let us say on the body surface, r equal to r, and this then gives v on the body into r. So, application of boundary condition then gives condition gives f x equal to v body, which we know is u infinity r dr dx. V body is u infinity dr dx into r. This is what the approximate flow tangency condition, which you have written many times. So, this gives the distribution of source strength for any arbitrary profile, and assuming that cross sectional radius cross sectional area A is pi r square. So, introducing this, f x is u infinity by 2 pi dA dx. That is for a body in axially symmetric flow, for a slender body in axially symmetric flow, the source strength distribution on the axis is simply given by the rate of area change of cross sectional area along the axis. So, what we get in source strength is proportional to local rate of change of cross sectional area of the body. Meaning that the portion of the body which are far away from the cross section or the corresponding concerned cross section has no influence on the local condition. That is, flow at any part of the slender body simply depends on the local cross section and its change. However, and the cross section which are far away, or the part of the body that is far away from this station, do not have influence on the local flow condition. In terms of perturbation, you can see that the rate at which the flow is perturbed due to pushing of the flow by the body away from it depends entirely on the local rate of change in area. Now, with this we can complete the solution for the potential over a slender body of revolution with closed nose and arbitrarily smooth meridional section is minus u infinity by 2 pi the rate of change of area will denote by a prime into log 2 by beta r minus u infinity by 2 pi a double prime j log of x minus j d j integrated over 0 to x. So, this is the potential for any slender body of revolution with closed nose and arbitrarily smooth meridional section in axial flow. So, this is the potential for slender body of a revolution with pointed nose and arbitrary profile in axisymmetric flow. In axisymmetric supersonic flow within the framework of small perturbation theory. Now, the velocity components can be evaluated that u by u infinity by differentiating that expression for phi with x. This gives u by u infinity is minus a double prime by 2 pi log of 2 by beta r minus 1 by 2 pi d dx of and v by u infinity is d is d phi dr, which gives a prime by 2 pi r, which becomes r by r dr dx. Now, C p of course, we can get the pressure coefficient is minus 2 u by u infinity minus v square by u infinity square. So, this gives a double prime by pi log of 2 by beta r plus 1 by pi d dx of this integration log x minus j d xi minus that is C p on the body surface, C p on body surface. So, we get the pressure coefficient on any slender body of revolution with pointed nose in axially symmetric supersonic flow. Now, let us come back to this pressure distribution once again. will consider a small section of length dx, and the free stream as we have mentioned m infinity greater than 1, the pressure here is P infinity, the pressure on the surface is P. At the back the pressure will of course be different, and we will call that base pressure. Now, the pressure coefficient that we have obtained corresponds to this pressure. However, as far as the back pressure is concerned, we cannot evaluate this back pressure based on this inviscid flow theory, because flow behind this body with a blunt base is always highly viscous, even may be turbulent, and cannot be evaluated by any inviscid flow theory. So, this P b can only be obtained using either a full viscous flow theory or by experiment. So, cannot be obtained from any inviscid flow theory. We need either a complete viscous flow theory, perhaps including turbulence, and or experimental determination of the base pressure. Now, looking to this area, let us say that in this side the radius of the cross section is r, then on this part the radius of the cross section is r plus dr dx into delta x. And projecting it on a plane, we get the projected area looks like two concentric circle. Projected area is basically two concentric circle. So, this projected area is becoming 2 pi r dr, and of course, it is a function of x, it depends on x. Now, the pressure acts on this projected area, and consequently, that force, the axial force this implies the axial force which itself is drag. In this case, or if we consider the total length of the body is L, then minus P B A B, where A B is the area at the base. That A B is base area. Now, this can be arranged in this fashion 0 to L P minus P infinity d A plus P infinity minus P B into A B. Then, if we divide this by that is, we are defining a drag coefficient based on the base area, not on the planform area as usually done in aerodynamics of wings or in incompressible flow aerodynamics, that the drag is always based on planform area, but in this case you can see that the drag coefficient is based on base area. Now, this gives when divided by half rho infinity u infinity square, this becomes the pressure coefficient. So, 0 to L C P d A plus C P B. Now, this can only be obtained from viscous wave flow solution or from experiment. This flow is cannot be obtained from inviscid solution. So, we can over this part, as we have already obtained, can be obtained by substituting that path, and let us call that C D 1 plus C P B, and this C D 1 then can be written as this we can write that A B into C D 1 is 0 to L C P A prime, which is of course a function of x into this, and then we substitute C P here from the earlier expression that we had to give 1 by pi 0 to L A prime x A double prime x log of 2 by beta r R is also a function of x minus 0 to L plus 1 by pi 0 to L a prime x d dx of a double prime xi log of x minus xi dxi. We may recall that this first and third term here has come from the axial velocity component, while this second term here we have come from the radial velocity component v square by infinity square in Cp. Now, this for convenience we will write as I 1 minus I 2 plus I 3. Sum of 3 separate integration. Now, the first term can be written as minus 1 by 2 pi 0 to L. We inverse this parameter of logarithm to get the negative sign log beta. Also, this must be beta r by 2 into d which on integration by parts gives us minus 1 by 2 pi square log of beta r by 2 0 to L plus 0 to L a prime dr dx square, which this term we can see cancels with the second term I 2. So, this I 1 minus I 2 becomes only this term. Minus 1 by 2 prime a prime square log of beta r by 2 0 to L Now, since we are considering bodies with pointed nose, so this becomes at 0 it becomes 0. So, it remains only the Hilbert. So, this becomes a prime at L square by 2 pi log beta r by 2, that is her r b is the radius at the base. The third integration as it happens is 1 by pi a prime x 0 to x a double prime xi log x minus xi d xi 0 to L minus 1 by pi 0 to L a double prime x 0 to x a double prime xi log x minus xi d xi dx and this becomes 1 by pi a prime L 0 to L a double prime xi where you have set the limit L for the length of the body, and at 0 we have used the properties of pointed body minus 1 by pi 0 to L 0 to x a double prime x a double prime xi log x minus xi d xi dx. Now, combining then we get finally when all three are combined, this we have E by 2 pi log 2 by beta r b plus a prime at L by pi 0 to L a double prime xi log of L minus xi So, this is the expression for the drag that comes in axisymmetric flow over a slender body with pointed nodes in supersonic flow due to the pressure distribution on the surface of the body, that is excluding the base pressure drag. Now, you can see here that these first two terms will become 0 if a prime L, that is the rate of change of cross sectional area at the base, is 0. First two terms are 0 if a prime L equal to 0. Now, what is a prime 2 pi r r prime? This then implies that or R L equal to 0. Pointed base. So, if the base of the body is also pointed, then the first two terms also become 0. Or if r prime L equal to 0, then body slope at base is 0. So, if the base is also pointed or the body slope at the base is 0, then the drag is given by the last term. Zero to L, 0 to x. Which happens to be that integration over a triangular area bounded by xi equal to 0, xi equal to x and x equal to L. So, we have obtained the drag coefficient due to the surface pressure distribution for a body of revolution with of slender cross section with arbitrarily smooth profile and at pointed nose. Subsequently, I have seen that if the base is also pointed, then the drag term becomes simpler, and similarly, if the slope of the body at the base is 0, then also we have a simpler expression for the drag coefficient. Now, this simply implies that drag coefficient will not change if the base cross sectional area is not changed. That means, if the base is extended or rather if there is a shoulder and subsequently a constant area part of the slender body, then that uniform part of the body does not contribute to the drag coefficient. That is, if we have say think about a cone cylinder. So, this part where over which there is no change in cross sectional area does not contribute to the drag coefficient. And hence drag.